Hey, this is Lance from LangChain. So Meta launched Llama 3.1 today, which was a really anticipated drop. And I'm going to show how to run it locally, how to build a corrective RAG agent that'll run locally using it, and how to benchmark it against a few other models. So the blog post announces a few different things. So 128 context length, a few different versions, an 8b, a 70b, and a 405b. Now the 405b is really cool. It rivals a number of larger closed source models. We can actually look at the blog post here. So it shows valuations. This is the 405b compared to, GPT-4 Omni, Claude 3.5 Sonnet, comparable performance. This will be hosted by, I'm sure, Grok, Fireworks, and many other providers. And this is fantastic. I'm really excited to play with it. So that's the 405b. Now the 8b parameter models I actually really like for local. I'll show my system settings a bit below, but basically I have a 32 gig MacBook Pro, and I can run this locally without a problem, and that's really cool. Performance is quite capable, so it's going to be better than prior Llama 3, and indeed they report better than Gamma 2 and Mistral 7b and Struck. So that's exciting. We're going to go ahead and look at it today. Here's my setup. I have a MacBook Pro, 32 gig M2, so just so you know what I'm working with. And I've already done this. So basically, I'm going to use it with Ollama pull Llama 3.1. That's all I need to do. So I've already done that, and you can actually go over to the Ollama page. You can see, so this is kind of, we can select the model you want to work with. You can see the 405b, 231 gigs if you have enough, if you have enough space for that. But, look, the 8b, 4.7 gigs, this is like kind of the sweet spot. This is, the size I really like to work with for local. So you just have to do a couple things here. So I've already done this. I have an empty notebook. So a few pip installs. You're going to see we're going to use Tavily. That's a nice kind of web search tool. We'll use LangGraph to build our agent. I'll use scikit-learn to build my little vector store. LangChain Ollama is the package that we're going to be using to access Ollama. So those are some things that you need to install, and this, of course, notebook will be shared. A few API keys. If you want to use OpenAI embeddings, you're going to set that. You set your Tavily API key, and these are keys necessary for Langsmith, which I'll show. That's totally optional. If you want to do evaluations, you can use Langsmith, but it's, of course, totally optional. So here's what we're going to build. And this is kind of my go-to vibe test kind of little application. I like to build these little self-corrective RAG agents. There's been a lot of cool papers on this theme. The big idea is simply this. With RAG, you want the ability to self-correct for mistakes in retrieval. So what you do is you retrieve from a vector store, you grade the documents for relevance, and if the documents are not relevant, you can kick out and do a web search. This gives you flexibility. If questions are outside the domain of your vector store, you can still answer them using web search. And so it's a super simple kind of little toy agent that I like to test out different models with. So that's all we're going to do here. Really simple. So first, let's just walk through the code here. I'm going to build a little vector store. I'm going to index a few blog posts from Lillian Wang, one on agents, one on prompt engineering, one on adversarial attacks. I'm going to load the pages. I'm going to split them. I'll use a chunk size of 250. This is, of course, arbitrary. You can tune this as you see fit. Build my splits, and here's where I set my vector store. So I'll just use sklearn vector store. I'll use OpenAI embeddings, and you'll see why a little bit later. It's because I've done some other evaluations using OpenAI embeddings, so I want to keep it consistent. But if you want something that's fully local, I also encourage you to look at nomic embeddings. So this is how you can just use them. All you have to do, again, I noted up here, is basically in your installs, nomic local. So that's all you need. So that's if you want fully local embeddings. I'm going to build my retriever here. That'll kick off. Cool. And just as a little note here, I can kind of call my retriever, invoke, and basically I can ask any question, agent, memory, and this should return some docs for me. There we go. So we have some docs. So we have a working retriever from our blog post. That's great. So this is going to be my little web search tool. I'm going to use Tavily. Again, I set my API key above here. So this just works. I can use this web search tool to search the web. So here's where I'm going to set up a few different things. So this is just going to be, I'm going to use LangChain Ollama, import chat Ollama. Now here, I'm just going to specify Llama 3.1. Again, we already grabbed this. So if you look above here, Ollama pull Llama 3.1. I have Ollama running in the background. That's all I need to do. And then this should be available to me as long as I've pulled the model. So that's it. Now this is just going to be a simple RAG prompt. You're an assistant for question answering tasks. Use the following documents to answer the question. If you don't know the answer, just say you don't know. Okay, so that's just like a really simple basic RAG chain I'm going to build, and we're done. So that's our RAG chain. Now here is another component we're going to need. We're going to need a retrieval grader. So if you kind of think about the flow we did above here, we just defined our RAG chain. That's going to be this kind of piece right here. We also need a grader piece. We have built our vector store, we have a web search tool, and now we just need the grader. That's the final thing we need. So for this, I'm going to use something that's very convenient, JSON mode from Ollama. And in my grader prompt, I'm basically going to say you're a grader, assessing the relevance of a retrieved document to a user question. Here's the document, here's the question. If it contains keywords related to the question, grade as relevant. It does not need to be stringent. You're just trying to kind of filter out erroneous retrievals, give a binary score of yes, no, return it as JSON, that's it. So super simple, we have a grader. So that's really it. Now we have a grader. So we can go ahead and go down here, and now I'm just going to build my little LangGraph. And so you're going to see all we need to do. So LangGraph is a really nice way to lay out control flows. They can be kind of custom flows that you want to express some kind of agentic reasoning, right? So we're going to set up a graph state. Our graph state is going to contain a few relevant things per our chain. So a question, a generation, search, whether or not to search, yes or no, documents retrieved, and the steps that we're taking throughout our chain. So that's all we need to persist through state. We have this retrieve node. So basically each node is just a function. So I set it in the retrieve node. It pulls in state. From state, I can get anything I need. So all these things are accessible to me when I pull in state to each node. So I can get the question, I can get the documents from my retriever. I can note that basically pull in the prior steps I've taken, append this particular step, retrieve documents, and then return documents, question, and steps back to state. So that's all I'm going to do. And I'm just going to walk through my flow. So I'm going to have a retrieve step, and we can go back to our diagram here. We can kind of see this vector store retrieval is basically going to be retrieve. So that's kind of our first node is retrieve. Our generate node then is going to be this one right here. So again, we're going to get the question, the documents, call the RAG chain with the documents in question, append generate answer to the steps, and return. Same with grade documents. So this is going to be the step here. In this particular case, same kind of flow. We take the state, we get the question, we get the documents. Now, initially, we say we are not going to search, and we iterate through our documents. We grade each one for relevance to the question, and we get the grade back. Now, if the grade is yes, we just append the document, so that means it's relevant. If the grade is no, then we basically set our search flag. We say, okay, one of the documents is irrelevant, we're going to search, and we keep going. So we iterate through all of our documents, we assess the relevance, and we keep going. And finally, we have this web search node, which is down here, and this just calls our search tool. So web search tool invoke with the question, get the search results, add them to our documents, and return the state. This final thing is basically just this edge we set right here. So basically, we get the search state, which is either yes or no. If it's yes, go to search. If it's not, go to generate. So that's basically this logic right here. And you're going to see in 1 second here, this is the whole control flow. So this is where all those pieces come together, and it expresses exactly what we kind of drew out here in our cartoon, but this is in LangGraph as a kind of LangGraph custom agent or custom control flow. So you start, you do retrieval, you do the grading step, what we just talked through, to look at each document. Is it relevant to the question? If any is not relevant, we kick out, we do web search. We add the search results to our documents, we send the documents to the generate step, and then we end. That's it. Super simple, but I've used this in a whole bunch of different tests, and it's like a really nice vibe test for different models. So anyway, I like that. We have our little agent laid out here. So cool, we've copied all that over. We've just walked through it. And now we can just run it. So let's test it out. So what you can see right here, I have a little function. So basically, this config is something I can use with LangGraph. So thread ID is not really relevant here, but if you ever want to, for example, save the state of a particular execution, you can use threads to do that. And I talked about that in some other videos, so I'll link them below if you're interested in how threads work. But for this, all we need is we take our custom agent, we're going to invoke it with basically a question. We'll send that in. We'll kind of send in a question as an example dict here. We'll pass it into our function. And then we're going to go ahead and return the response, and that's it. So let's go ahead and test that out. So our agent is running here. And right now I can actually open up, I can go to Langsmith, I can open up my projects, we can see our LangGraph is running here. And cool, so we can see we've done the retrieve. We're looking at our documents, we're grading each one with Llama3.1 from Llama, so that's pretty cool. We confirm we're using the right model, and hey, this is pretty nice. This is all running locally. We're doing the grading, we're doing the generation, and we can actually look at what happens here. Cool, when we get an answer out. So this is pretty nice. We've been able to run our custom agent locally using Llama3.1 and LangGraph. We've used, actually, which is cool here, token usage doesn't matter. We're not being charged. It's running on my laptop locally. Latency looks pretty low. It looks like it's around 5 seconds. I guess that's actually, sorry, that's just for this particular run. The overall latency is, let's see, 16 seconds. Okay, not bad. So that's pretty cool. All right, cool. So that's good. We know everything works. Now, let's actually do a little bit more evaluation here. So what are some things I can do? If I want to kind of really benchmark this rigorously, I can do a couple different things. So basically, I can look at, the end-to-end performance of my agent. So basically, is this response correct relative to some reference? And I can also look at the sequence of actions that it took. So is it taking the right and expected number of steps, which you see I log here. So I log the steps it takes, retrieve, grade, generate. So that's cool. I log that. And I log the response. So actually, I can evaluate both. I can evaluate the end-to-end response. I can evaluate its sequence of steps, right? So that's pretty nice. Now, I'm going to set up this evaluation section of the notebook here. And what you're going to see here is I'm just going to define a function. So this function is going to be my evaluation for end-to-end performance. I'm going to use a basically LLM as grader. Here is the prompt that I will use to grade my generations. This is in the Langsmith hub. It's something like this. You're a teacher grading a quiz. You're given a question, a ground truth correct answer, and a student answer. Grade it only based on the factual accuracy. Ensure the student answer does not contain conflicting statements, and so forth. A score of 1 means it meets the criteria. A score of 0 means it doesn't. So a binary grader, we're going to run it on our reference answers relative to our RAG generate answers. So that's what we're going to have here. And I'm also going to do a custom evaluation function for my trajectory. So in this particular case, all I need to do is I get the tool calls out from steps. So basically, if you look at what I return here, I return this dict. It contains steps. So I can fish out the steps right here, get the tool calls, and simply compare them to what I expect. I either want retrieve, grade, web search, generate, or retrieve, grade, generate. Those are the two trajectories that I expect my agent to take. I can extract those tool calls, and I can just do simple comparison. Does it match one of those two? If it does, score 1. If it doesn't, score 0. So that's really it. Now, only thing I left out here is that previously I've already built a data set, and I'll go ahead and show you that right now. So I'll go down and show this. This is all I've done to create a data set in Langsmith. I'll just put it in here for fun. So this is my little data set that I'm going to use to test. So you can see it's really easy to build an eval set. Just a set of question-answer pairs. Question, answer. So these 3 are based upon the blog posts that I've indexed. These 2 are just current events. So I want to make sure my corrective agent can answer questions about my blogs in the index and also answer just current event questions about NFL draft or the NBA finals, right? So this data set I've already created. It's named corrective RAG agent testing. If I go over to my Langsmith, so I go to my data sets and testing, it's right here, and I've already run a few experiments on it. But it's here. That's the nice thing about it. So I have this data set. I've created it. So that's all really nice. Data set exists. I've set up my evaluators. So this is what I can use to evaluate kind of the tool call trajectory. This is what I can use to evaluate the end-to-end answer. And I go ahead, and this is all I need to run. So basically, there we go, and I can kick this off. So now my eval is running. All I've done is I've set my data set name. This is just some metadata about the model I tested. This is just like my experiment prefix. So that's custom agent answer is the function that I built right up here. Boom. So again, that's just going to take in an example dict, and it's going to pass the question from the dict into my chain and get the answer out. That's it. Return a response, return the steps. That's all I need to do. So this is running, the data set's there, the evaluators are specified here, and this is just metadata. I also tell it to run 3 repetitions. So that's really it. Great, so that ran. And this is just a logging of the tool calls that I make at each iteration. So there's 5 questions. Each one of my evals runs 3 times. So that's 15 total. Now let's go over to Langsmith. We can actually look here. So I've run a bunch of different evals with other LLMs already on this data set. So it's kind of nice for very quick, kind of like sanity checking, right? So you can look at the names here. These are the experiment names that I've run, all in the same data set, all with 3 repetitions. Again, super quickly, I can just look at my data set here. So there's 5 questions, right? So that's fine. And here's my score. So this answer versus reference, if you go back, right, this was what we defined here. So that's this answer evaluator. Answer versus reference we set as the key here. And this is just using LM as judge to compare the reference answer to our LM generate answer, right? That's all that's happening here. And then this tool calls an exact order score is what we define down here. And that's the key here. And again, this was just saying, hey, do the tool calls follow either one of these 2? That's all it is, right? So here's the story. This is what we just ran, Llama 3.1. My answer versus accuracy score is 80%. And that's run against 3 repetitions. So 80% overall. Pretty good. And the tool calls 100%. So it's always calling a reasonable tool trajectory. So that's good. Total latency around 8.6 seconds. Not bad. That's the P50. P99 is 12. So reasonably quick. Now let's compare that to some other models, right? So here's Llama3.1-8b. So this is the Llama 3, not 3.1. This is Llama 3, the prior one. So you can see performance is different here. 60% versus 80, so we've improved performance. Latency, 18 versus 8. So it looks like latency is indeed lower here. So that's great. Pretty cool. So basically it looks like 3.1 is a clear win. Performance-wise, latency-wise, it's also very reasonable. Now, this was pretty interesting. I can compare locally running Llama 3.1 to Fire Function v2 with the same architecture. So this custom agent thing is what I want to be looking at. And this is with Llama 370b, okay? So we can see is 3.1-8b running locally performs the same as 70b through Fireworks. Pretty cool. So the 8 billion with 3.1 is on par with 70B on this particular challenge. Latency is not much worse. Running locally 8.6, running via Fireworks 6.37. Of course, it's running a larger model, but look, you're getting the same performance on this little toy challenge with only a little bit more latency. Pretty cool. Now let's compare. You can look down here. Let's look at custom agent with GPT-4o. We'll not worry about the Reacts for now because it's a different architecture. So let's just look at the custom. So I want to compare GPT-4o. So 4o, same performance, right? Same tool calling. So basically, parity in performance, and indeed, latency is lower. Fair enough. So it's 5 seconds versus 8. But look, the punchline is this. Local model, on my laptop, free, same performance on my little toy challenge, of course, right? This is, again, caveat, just my little vibe test. Same performance as I get with much larger models, 4.0 and Fire Function v2, with only a little bit worse latency, 8.6 versus 6 or 5 seconds. So again, just gives you a sense, like this looks like a really good model. I love having these little 8 billion parameter models for local testing. I'm excited to try kind of more sophisticated local workflows with it, but again, I think this sets kind of a new bar for local models. And this just shows how to run it with LangGraph for a custom agent. And again, all this eval stuff is totally optional, right? You know, the key thing to look at if you just want to build an agent, just look at the LangGraph code all up here. The evaluation is just kind of how I do my vibe tests. And I would encourage you to look at evaluations independently, but that's not totally central for what we're showing here. What we're showing here is the ability to, I'll go back to the very beginning, build a locally running self-corrective RAG agent with Llama 3.1-8b that runs locally, and we've been able to do that. So again, encourage you to play with this. It seems really promising. Thanks.